Thanks for coming. This talk's called Fixing the Watchdog, How Open Documentation Empowers Community-Driven Hardware Support. Who am I? I didn't put my name, I think, anywhere in the presentation, I'm realizing, but I'm Andrew Halaney. I work at Netflix right now, mostly doing container runtime stuff lately, but in the past, I've worked like 8 years on automotive systems, doing kind of everything, but mainly hardware bring up, so like PSP integration and like kernel driver support. And today, I'd like to talk about kind of that world a little bit more, and specifically documentation. So I really want to just try to kind of emphasize that open documentation really enables the community to self-service. I think that's like the big theme I want everyone to get out of this, and like I hope to show some good examples and make you think about, you know, either the suppliers you're working with and if they could be better, or if you are a supplier, could you do better? Yeah, and to do that, first we're going to get, I don't know, a little philosophical, why talk about documentation, then create like a silly framework to kind of analyze docs. We'll look at a few bits of documentation. Then I'll look at, we'll go through a real world example of TI's J784 S4 EVM, mouthful, docs, and how they enabled me last year to go ahead and fix the Watchdog and various other subsystems within the SoC without needing to involve TI at all. So first, you know, like I said, a little philosophical. Why does documentation matter? You know, it's the connection between supplier and community. Without docs, no one knows how to use whatever your product is. I'll be focusing a lot on hardware docs today, but this does apply to software documentation too. Like, you know, in the Linux kernel itself, there's the docs folder, and if you contribute to the kernel and you haven't contributed to the docs folder, I think you should. I bet you read things and thought this could be written better. It should be a key factor when you're evaluating suppliers. I think it's often glossed over, so software support really often, unfortunately. But whether you're a hardware guy or software guy, like you should look at both angles. Is the hardware documented well enough that the hardware guys can do their job, and can the software guys do their job? Another way to view that is this applies to both hardware docs, or like hardware suppliers and software suppliers. So if you're buying a service, like is it documented well enough that I can properly use it? You know, like I said, I want to talk about this just to kind of motivate people to think a little bit more about their docs and how it could help them. You know, I think TI got free work from me out of this, and they didn't. You know, it was out of the goodness of my heart. We'll call it that. But yeah, and then yeah, there's documentation's alive. We can always do better. You can fix docs upstream. You can give feedback to, you know, your suppliers, and if you're on the other side of that fence, you know, you can release a new revision with better docs. So just to kind of like put ourselves in a framework of how are we going to score some documentation, and then later try to keep that in mind and say, oh, since this scored well, it's easy to work with. I came up with some simple characteristics that I like to view. The first one would be completeness. So, you know, like how in-depth does this go? A good example, it's kind of fun that this is at the end of the conference because I've gotten to sit into a bunch of other ELC-related talks. The soft ISP talk today mentioned the sensor documentation, and Hans had highlighted how kind of useless the docs were because they're very complete, but it just said like this bit represents this signal, and you don't know what that means. So that kind of moves to the next point, which is it comprehensible? You know, do you have enough background that you can actually use the data that's provided in a useful way? And this is like, you know, where diagrams and visuals come in hand. Kind of in the same vein, organized and searchable is a big deal. With big, you know, SoCs, you get a lot of docs, and one, where to find them, and two, which docs are relevant can be really tough. And then, you know, we're in the age of AI now, and LLMs are everywhere. You can kind of shove docs into an LLM and get like a quick pointer, which is actually pretty useful now. Fortunately, for this talk, I didn't have that luxury last year, but in retrospect, that'd be nice. And then the big one to me is availability. So is it public? Is it behind an NDA? Is it internal only? You know, I've dealt with all flavors of this in my career, and the closer you are to public, the more like the developer experience is going to be much better all over. More likely to have a community of users out there. A good example, like I'll reference later in the talk, is like TI's forums public. So I was able to, just find some people talking about similar issues that I was having. And yeah, I think this kind of is a catalyst. It's the salt on the food for the other categories. If you're available, like the impact that your complete and comprehensible documentation has is much greater. So we're gonna go through like real quick some like easy examples of using this framework. All this is available, obviously, otherwise I couldn't show you the docs. But so just keep this in mind that on one hand we have comprehensibility, another one we have completeness. So say someone gives you this doc, it's like a functional block diagram, and there's some bullet points, and they'll be like, oh, the J784S4 comes with, I don't know, Cortex A72 for your processing needs, and a bunch of DSPs for machine learning purposes, and oh, there's a GPU, and timer subsystem with a Watchdog, which is what I'll focus on later. Where do you think that lands? Think to yourself for just a second. It's comprehensible, like if you know the terms I just mentioned. If not, it might not mean anything to you. But it's definitely not complete. Like I couldn't tell, like using that, I wouldn't know how to enable the Watchdog or use it. But I know what's on the product. Going a little further, here's a board assembly drawing. So this is, like if you've never seen one of these, this is the top down of what the PCB actually looks like. And the resolution is really bad. That's my fault. But like all the components are labeled. So if you have the schematic as well, let's say you do, you can find something on the schematic and verify that it is indeed populated and it's the correct component. You could probe it if you need to. So where do you think that would land? I said it's pretty complete. You could argue it's more comprehensible than I gave it. I would say without a TRM, you don't know what the ICs are doing. So like the signal, why is this line bouncing up and down? Who knows? Yeah. Now, everyone's gonna close their eyes and I'm probably gonna just run away. Just kidding. But imagine you got the other bits. You've got, a TRM. It's open, it's got functional block diagrams, it's got detailed descriptions. You've got an Excel sheet that gives you all the register settings, power on reset values, signal routing, that kind of thing. Where would you put it? And, drum roll, I'm sure you all know where this is going. It's top right. This is good. And that leads me to TI's J784S4 EVM. It's a eval board by TI that I was working with a few years ago. It's automotive targeting. They have public docs, and they're pretty complete, and they're pretty comprehensible. It's really nice to work with. There's upstream support, so I could run Fedora on it, that kind of thing. But the documentation was really what blew me away. I didn't have to make a login even, which is, I don't know any other vendors really that are that good on that front, especially in automotive. So this kind of describes the hardware. We already went over it. It's not super important, but you got a bunch of Cortex A72s that you would run Linux on. You got some DSPs for machine learning purposes. They got a bunch of R5s for like microcontroller use cases, one pair is in a different power domain. Basic system services, this handles like clock stuff, which will become relevant later. And all your normal connectivity stuff, GPIOs, UARTs, all that jazz. So the situation I was in was, I was given this board and they were like, oh, you need to, run this demo that we already have out of the box. Like, go ahead and get it booting our, upstream and then put the demo on it and make sure everything works. So the first thing you got to do is figure out how you turn the board on. What the heck is this thing? So you start looking at the docs. And this is one part that could be better about TI's docs, in my opinion, is, well, I think all docs suffer from this, but like, where do you go? It's really tough. There's like a bunch of different docs, and you jumping through the links, you don't really know what's important. This, in my view, as someone who's worked with it in retrospect, if you just laid this out to people, they would immediately kind of know what they need to do. So at the board level, the eval board provides one big zip file with bill of materials, the schematic, assembly drawings, that kind of thing. So if you need to like get on the physical hardware or see where things are going, that's where you go. If you're just trying to turn the thing on really quick and figure out what all these dip switches do, They have a quick start user guide, which is useful. And then if you need to get like into the processor and learn about things at the SOC level, they have a TRM and Excel sheets with, like all the stuff I mentioned earlier, signal routing, register settings, that kind of thing. They also have a BSP, which is also conveniently easy to use compared to a lot of vendors, in my opinion. You can compile it in a container, just Yocto. Their U-boot K3 docs are pretty good. I actually contributed in the review process for getting those upstream because they messed up the dip switch originally, and we got that corrected. So let's walk through kind of what those docs look like real quick. This is a snippet from the user guide. I'm not going to show you text. That's not as fun. So I'll show you a picture. This is convenient because you bought an eval board to say like, is this SOC good enough for me? Does this meet my needs? And you need to figure out what you can actually do with it. So like over here, let's say I wanted to do a dead reckoning application. I have an accelerometer and a gyroscope, and I can figure out what bus it's on really quickly just by looking at this, which is more convenient than pulling up a 120-page schematic and trying to dig through. Eventually, though, you do need to go to the schematic. And I do like their schematic. They have some high-level intro stuff early on, which is nice, so you don't have to like look at 20 capacitors in a row and get a little overwhelmed. But when you need to get like nitty-gritty, it's all there. You can see these are 10 microfarad capacitors, and they've got a bunch of PCB designer notes if you're on the electrical side. If you're on the software side, you can see like possible I2C addresses this thing can be in, that kind of thing. Going from the schematic, let's say I want to find a test point or I want to find a resistor, Control F and it'll be on here somewhere. You'll have to zoom in and push your glasses up like I tend to do. The TRM level, every section kind of gives you a nice functional block diagram and then detailed description. Nothing crazy, but it's nice. Like this is comprehensive, and then the description below like kind of completes it, in my opinion. The Excel sheets are kind of overwhelming to navigate a little bit, but there's really good info in there. So this, for example, is saying that whatever RTI 0 is, which ends up being the Watchdog, has interrupt ID 240. So if that is useful information to you, you've got it. So like I said, we're trying to run, and we being ex-colleague of mine, Eric Chanuday, who also helped me upstream some of this stuff, so thanks to him, by the way. We were trying to run this demo, and one of the things we do in the demo is lock the system up and show that, it can recover. And how does that work? If you're not familiar, hardware Watchdog is typically responsible for that. So it's a bit of hardware that you can, once you set it up, you have to pet it in a certain period. If you don't do that, it'll kick the whole system over. The interface for the kernel is documented. Could be probably documented a little better, but it's a pretty simple interface. You just write to /dev watchdog, and that's how you service it. There is a I/O control interface for like setting the timeout and other things like that if you need to adjust those values. Luckily today we don't need to do that. This is what it typically looks like, and I think most people's setups at least is, let's say you have critical app.service. It's run by systemd. You can set up software Watchdog with systemd, and you talk to systemd via SD notify call. So you say like, hey, I'm still good. Everything's good. I'm not in a deadlock or anything like that. If it does happen, systemd will restart you. And then you can set up systemd to write to the actual like kernel interface and interface with the hardware Watchdog itself. So systemd will just do a simple write. It'll go through the kernel, through the driver, and on this hardware at least, the hardware Watchdog is accessed via MMIO. So we tried the demo and it didn't work, so I was like, what the heck? So I got on the command line and just tried to pet the Watchdog myself and then not pet it. You see this like the classic test is you just echo a random foobar into the Watchdog and then wait for the system to kill you. That didn't happen, as you can see here. So I echo empty string in the Watchdog. The kernel yells at me and says, hey, just because you close the file doesn't mean you can stop petting this Watchdog. You need to keep petting it, or else bad things are going to happen. The system's going to be reset. Then I started dumping a bunch of the sysfs information about the Watchdog. Min timeout being 1 and max timeout being 0 made me raise my eyes right off the bat. The state was active, which was good. Timeout was 60 seconds, and time left was 1 second. And if I keep printing that in a loop, nothing changes. So it seems like this thing's not really ticking. So like I started thinking to myself, where do you go when you have this problem? What do I look at? I could contact TI and deal with vendors, which can be good or bad. TI's been good, admittedly. Like I'm not trying to shame them, but I'm like competent enough that I feel like I can solve this problem myself. And I have all these docs; they're complete, comprehensive, available. Let's do it. So first off, since it's a problem within the SOC, you got to go to the TRM. So I go to the digital windowed Watchdog docs within the TRM. That's the subsection it's in, and they give you a good guide. Basically, how the hardware works. Don't try to go programming anything just based on this quick description, but is once it's enabled, this preload value is loaded into a counter. That counter ticks based on an input clock called RTIF clock. When it hits 0, it goes to reset the system. If you don't want the system to reset, which is the usual case, you would then write something in this Watchdog key, a specific sequence, and that will trigger a reload of the preload value, so you get another period to stay alive. If you mess up and don't write the proper sequence, that'll also reset the system, so they don't want some rogue software accidentally writing to the Watchdog and keeping the system alive even though you're in a bad state. So pretty simple. When you think about like this diagram, and the fact that the timer's not moving, I think one of the natural things to think about is the input clock, and that's kind of where we're going to end up going. So you keep these docs open, then you pull up the driver, which we're not going to do today, and you look and see, how's this thing set up. Like I said, it's hard-coded on a 60-second timeout based on the input clock, so it gets that from the clock subsystem, which ultimately is all selected via device tree on this platform. There's actually a window for petting, which is not super relevant, but there's a 50% window, so like if you pet outside that window, it doesn't count. Not relevant because I want the system to reset. That's not my issue. It's not resetting. There's an interrupt enabled, but there's no handler and there's no description in the device tree. Makes sense. I mean, it's a Watchdog. You're not going to handle the interrupt. You're going to get the system reset. So it's kind of maybe a convenient debug tool. I had the driver in hand, and I was like, maybe something weird's going on with how the clocking works. I don't know. Let's just write an invalid Watchdog key sequence and see if that works. No luck. So I go verify how it reads time left just to make sure I wasn't being lied to on like the ticking down value, and indeed it was reporting the same thing from the register no matter what. So start thinking, what makes that tick? Is there any kind of violations? And indeed that was the case. Looking at it, the input clock that was selected for RTIF clock was running at, 19 megahertz or something, and it's supposed to be in like the kilohertz. So fix for that is to just change the clock in the device tree. It's not that hard. Christoph will help me out, But what was nice was their clock interface is abstracted by firmware. They call it the system control interface, and they actually have public docs for that too, which we're not going to go into, but they work. I mean, they're not the cleanest docs, but they're better than a lot of vendors' firmware interfaces, which don't have any docs, and you just look at the downstream and copy the values and pray everything's fine. So yeah, got a patch for that. So then we go back to testing again, and the Watchdog ticks now. So I'm like, okay, nice, we're gonna get it. And then it gets to 0, and I went upstairs and got coffee, came back down, expected to be back at the prompt, and instead I just see zeros on the screen. So we don't have liftoff, and I'm starting to get mad. So the next step I thought was, okay, let's make sure, okay, it reached 0, the counter's working, but how can I verify that this thing's actually in reset before I move on and try to figure out what's going on? So one way is they talk about in those Excel sheets, which is kind of where things get complete in our framework. They talk, have register descriptions, and one of them is the Watchdog status register, which says that bit 1 indicates, if set, that a timeout period has expired, and further up you can see that a reset event is generated. They also have another one for the Watchdog key, which I don't really use in this example, but it's there. The other thing that I thought was, this is kind of, was overkill, but I was like, there is an interrupt enabled. I don't know how that, the reset logic works. Maybe it's tied to that interrupt. Let's go ahead and like enable that with the interrupt controller, the GIC, and just print something when the interrupt fires to see is that working. So I go ahead and find it in here, and it's interrupt ID 240, and you have to do some translations in the device tree and add a simple handler, but that's easy. And with all of that in place, you reload the kernel, try again. So you can see here that I'm printing the Watchdog status along with the time left callback. It's 0 at first, which means there's no reset event, which is okay. Like enough time expires that I expect it to reset. I get a bunch of interrupts fire off, which is good. That's indicating to me that this thing does think it's in reset. And then reading the Watchdog status, now it reports O by 3.2, which if you do your your binary analysis stuff, bit 1 is set. That's what the 2 means. So this thing is indeed in a timeout violation reset event situation. Okay, so we know the Watchdog's working, and now I'm thinking, where does this reset go? I'm trying to look around in the TRM. It's not super clear. Eventually, I finally grepping around for RTI 0, see in that Excel sheet that it's connected to this ESM 0 thing, and going back to the TRM, I finally find what this ESM 0 thing is. I also find that there's a whole what do I call it? Module integration section, of how these bits are connected, which is nice, but it's something I missed. That's typically a problem I find in TRMs is each bit of IP is documented by, I don't know, whoever the design team is for that IP. So it's very specific to this IP, and it's not talking about the actual system integration level. So you can have a hard time connecting the dots. So I need to find out what this ESM thing's all about. Luckily, repeat the same process as prior. It's got its own section in the TRM, and it's also in the module integration section. So on the left, we can see this ESM stands for error signaling module. Is just a multiplexer. It takes a bunch of inputs for errors and outputs one error. You can see that on the right here, there's actually 3 of them, 1 for each power domain in the system. So it goes from the least critical to the most critical. So ideally, you'd probably just want to enable all these. And then it's also clear from the docs and the wording around it that these are the outputs, MCU safety error N and SOC safety error N, and they leave the SOC. So we're going to have to go to the board if we need to debug this further. So I start examining this bit of hardware. And, this is where the openness helps too. You Google ESM real quick and you see people complaining on forums because you only get complaints online, unfortunately. But so I know where it is. People are referencing it in U-boot. There's already a driver for it. Just a matter of setting up the platform integration to say actually turn all these on. There's a couple different hardware domains, and they have 2 different U-boot stacks essentially running depending on which domain you're in. So you have to do it for both. So I did that. Retested again. Still no luck. So I think, well, I can try to read from the ESM, but there's not a lot of great status registers, and I was starting to get impatient and wanted to see the full picture here because I thought maybe this is going to just take me forever. So I said, let's go out on the board and see what that looks like. So now we leave the SOC documentation and we go to the board. You pull up your schematic. It's 120 pages or something. So you have to use Control F. You Control F for the signal name. So if you recall from this slide, we're looking for MCU safety error N. So I Control F. I get taken to this page. You can see right here, here's MCU safety error N. It goes to page 30 as well to something else, which we'll go to in a minute. There's also a test point right here, TP315. So it's a little piece of metal that you could put a multimeter on. You can see over here that this is, in fact, the SOC as well, J784S4. It's just a functional representation of a small part of it. Since it's got a ton of I/O, you can't put it on one page. And then here's the other one, SOC safety error N. So I, trying to validate, are these being asserted, which means are they reading 0 volts? See where that goes as well to make sure, does this even make sense, or did they kind of mess up the hardware design? So you go where it goes, Control F again, page 30 here. You can see that GPIO 7 is connected to our special MCU safety error N line that we're really interested in right now. GPIO 7 is on this TPS 6594 thing, which we now know who to bother about that if you need any help. And you can also see that it's a PMIC. So you can Google it real quick, and you can find a doc on that as well. It's publicly available. It's nice. And it's available addresses are these, and if you look, it's actually set up to just use hex 48 right now. But I pull up the doc, and it's like 100 pages or something, and this is like the third piece of documentation. I thought this was going to be quick, and when I saw the Watchdog, I thought it all worked. So I paused for a second and say, let's make sure the ESM works before I start reading about this, because if what I just did made no impact, then I'm going to be debugging the PMIC for no reason. So, follow your connections, the signal chain, and verify the whole way if you can. So we have everything we need to physically just probe the board. Like we've seen where the signal goes. There's a test point even, so I don't even have to, deal with a tiny like 0204 or anything like that resistor. I can just hit the test point. So let's kind of walk through that process in case you're not familiar with it. It's kind of fun. It brings you into the real world and no longer just pictures of schematics. So back on this page again, we have the test point TP315. I want to make sure that once the Watchdog resets, this goes down to 0. And when it's not reset, it's high. So 0 is, we're in reset. I try to figure out where that is physically on the board. If you have looked at a PCB, you would never be able to find that like via your eye. Luckily, they do have silkscreen, so you technically could, but it would still be really, really hard. And if you work in embedded, I bet your hardware designers stop putting silk screens on like really fast and like save some money, and then you're kind of mad. Anyway, so you go ahead and look at this. Control F again. It's super tiny. It's down here. Zoom in a little bit. You see that, okay, this is this TP315 right here, so this is what I need to probe. Try to find some kind of, reference points to when you look at your board so you can find this thing, because it's going to be really small. And then you walk around in your socks in your basement, if you're me, in my home lab, and you look at the board. Here it is. Kind of looks like a hot car shot or something from this angle, but yeah. You go ahead and orient yourself the same way that the assembly drawing is. You find the components you were looking at, and you start squinting a lot. You zoom in, or face right up against the board. And you can find the test point, which quality here this is my fault, but this is TP315. So this is what I need to probe. So then you do like a game of Twister, where I don't know if you guys saw where my laptop's like around the corner here, and this is kind of a nightmare cable management situation. So I'm over here with the multimeter, like hitting enter on the laptop, and like trying to spin it around so I can see when it goes down to 0 seconds and fires the interrupt, and I expect it to go low. And voila, it does go low. So I know that so far everything I've done is working, and I could submit those patches if I wanted to, but of course I was probably going to get the whole thing working first. I also went back and undid the patches and made sure that it stayed high. So like that was actually a necessary change, and I'm understanding what's happening in this system, which is always good to double check. Yeah, and then last but not least, the PBIC enablement. So that safety RN went into GPIO 7. So let's figure out how this PMIC works. It's on an I2C bus, so you got to make sure I2C is enabled. And that actually kind of burned me. It looked like it was enabled, but in U-boot, with the way some of the stuff comes in from device tree, it was actually kind of mashed out. So I ended up debugging pre-serial console for a while without JTAG, which is painful. Ended up just dumping stuff to a buffer and then like ignoring some errors and dumping it later and to figure out where the problem was. It was just a regulator wasn't described for the I2C bus, and it needed it, and so it failed to probe, and then nothing happened on the board. But anyway, once I got I2C working, and there was a driver for this PMIC already, so I just needed to kind of sync the two up. But how the driver works is pretty simple as well. There's just an enable bit, and then after that, there's a state machine that works. So at the right here is the pin that we're sending to the PMIC. When it's high, it's not in an error state. Remember, when it goes low, it is in an error state. The red is kind of confusing here, but it's still low. And if it remains low for a certain period, then the PMIC bounces this reset out pin, which is supposed to reset all your power supplies and take the whole system down. And finally, with all that in place, I rerun the test and the board reboots, and I'm happy and ready to submit my patches. So just I kind of have 2 recap slides, I guess. But what we just did was we walked a little bit of Watchdog documentation from the kernel. Like I said, that's open, public, complete. Could be better, could be worse. The SOC documentation, we looked at, the module integration section, which is kind of nice, and I wish would be more front and center maybe, but maybe I should just RTFM a little bit better. We looked at, the Watchdog documentation, the ESM documentation, and we left the SOC. We looked at the board documentation they provided. We looked at the PMIC documentation, which I was very happy was, open. I thought as soon as I saw it went to another component that's not related to the eval board, I thought I might be in trouble and wouldn't be able to get the docs, but luckily, that wasn't the case. In each step of the way, this is a kind of I would call systematic debugging process at least, and I think the only reason it was so systematic and not kind of blindly poking was because the docs were complete and comprehensible. I could, verify each step in the signal chain, what happened. And they're available, so when I submitted my patches, I could quote the docs, I could link to them and say, go read this. Which there wasn't really much contention in this, but I've had past experiences in the Network PHY subsystem, for example, where Russell King is asking me, how does this work? And I don't have enough documentation to explain to him, and I also don't understand the subsystem well enough to know how it should work. So this kind of thing's really advantageous because I could just send him the docs and be like, can you advise me, please? And he totally would. And this was just a good experience. A lot of times, as an integrator, you don't get a lot of opportunities to do real engineering. A lot of times it's just copy paste, look at downstream code, try to figure out what's going on, but you don't know how that hardware is actually supposed to work. I didn't have to bug TI. I mean, they eventually reviewed and helped me merge this stuff, but they didn't know there was a problem until I finished submitting the patches. And the tooling also was really nice. The SCI tooling is, it's nothing amazing, but it's open source and usable and easy to compile. Flashing the board was easy. There was no proprietary protocol or anything that you deal with sometimes on other vendors. Yeah, I guess the other thing to highlight, I already mentioned that with the SCI stuff and compared to other vendors. Yeah, there's a power management talk about power domains that may have already happened, may not, and I think they're going to talk about these kind of interfaces, and I find it convenient that this interface is at least documented and available to people versus some other more opaque firmware interfaces. So final recap, why was this an easy process, and why was I able to do work for TI without harboring any annoyance with TI? It didn't hurt their position in my head. If anything, I thought this was a good thing for them, is because the docs were complete, comprehensive, and most importantly, available. Tooling matters. It falls into this category as well. There's always opportunities to improve. I improved the docs along the way. I encourage you, even outside of hardware documentation, if you work in the kernel and you've never submitted a patch to the documentation subsystem, you're doing something wrong. You really, really have no excuse. You have definitely read things that were written poorly, and you can improve. Yeah, and then make sure you consider this stuff when you're selecting a supplier, be it hardware or software. Your experience is going to be way better. There's bazillions of talks about how writing upstream is so much better for security updates. If you're on an automotive platform, you're going to be stuck, I don't know, 10 to 20 years maybe, depending on who you're working with. And good luck porting your vendor BSP that doesn't, because of its lack of documentation, no one can get it upstream. It's going to be a bad time. So with that, I'd like to thank Eric from Red Hat, who helped me make some of these patches and debug this, and Reek from Red Hat, who tested the patches on a sister board that TI makes, the AM69. So this kind of all enabled that as well along the way. Udit from TI, who helped get these reviewed and merged, and Nishant as well. Anyone got any questions? Sweet. All right, thanks, guys. I appreciate you coming. Feel free to talk to me about hardware or container stuff. I'm here flying solo, so yeah, happy to chat with anyone. Thanks.